All right, so we now take a look at what happens with mixtures of gases. If you think back to the beginning of this chapter where we talked about the fact that gases and mixtures of gases don't really care about their neighboring molecules, then it might not surprise you to realize that there's actually not a lot of real significant effects from mixtures, and the only real impact is from the quantity. And so if we have a mixture of gases, each one of those individual gases will have its own pressure. And you can calculate those individual pressures based on the ideal gas law. Just the number of moles of one of those substances times R times T over the volume. And if we add all of those pressures together, we get the total pressure for that mixture. And so this equation, pressure total equals P1 plus P2 plus P3 plus so on, is known as Dalton's law of partial pressures. Now, how do we calculate the partial pressure? Well, we need what's known as the mole fraction of each component. And the mole fraction is this quantity in this equation. So the pressure of each individual gas is equal to its mole fraction times the total pressure. And we can find the mole fraction of any substance, whether it's a gas or not, by taking the moles of that substance over the total number of moles. Now notice that when we calculate this, and we'll do an example in a moment, that mole fraction is going to be a calculation that is moles divided by moles. So what are the units on mole fraction? There aren't any. So we can look at the following situation. A 2.5 liter flask has 12 grams of carbon dioxide and 15 grams of oxygen at 298 Kelvin. And we want to know what is the partial pressure of carbon dioxide and what is the partial pressure of oxygen. So in order to do that, we're going to need to know two things. We're going to need to know the total pressure of the gases and the mole fraction of each component. So I've started here by calculating the moles of carbon dioxide and the moles of oxygen. This is a calculation we've done many times before, and we should be pretty comfortable with this calculation at this point. If you aren't comfortable with this calculation, you may want to go back to some of the previous chapters and review some of our calculations of moles that we've done previously. Once we have these moles, these mole values, we can calculate our mole fractions. And so our mole fraction for carbon dioxide is going to be the moles of carbon dioxide over the total number of moles, which is the moles of carbon dioxide plus the moles of oxygen. And so we get our mole fraction of carbon dioxide is 0.368. And again, there's no unit on this number. For the mole fraction of oxygen, we can do it one of two ways. We can do the same thing we did above and use the moles of oxygen over the total moles. And we'll get 0.632. Or to find these mole fractions as we add each of them up, the sum of all of them is always going to be 1. So we could have just taken our mole fraction of carbon dioxide, since there's only 2 components here, and just subtracted it from 1, and we would get the same value. All right, now in order to find the pressures, we first need to find the total pressure. The total pressure we can get from the ideal gas law. Recall our number of moles we've calculated, and this is going to be our total moles because we're looking for total pressure here. Times R, and just so I don't run out of room, I'm just going to leave R there, times the temperature over the volume of 2.50 liters. Now do note at this point, if instead of the total pressure I had just stuck in, or the total moles, I had just stuck in the moles of carbon dioxide or the moles of oxygen, that would be another way that I could find each partial pressure. But I've already started this way, so we're just going to move on. So our total pressure here, 7.26 atmospheres. So I can use that now. The mole fraction of carbon dioxide was 0.368 times that total pressure that we just found, 7.26 atmospheres, and we get the partial pressure of carbon dioxide, 2.67 atmospheres. Now again, because we know the total partial pressures need to add up to the total pressure, the easiest way to do this is we can say that P total is P carbon dioxide plus PO2, or that PO2 is equal to the total pressure minus the pressure of carbon dioxide. And we can just calculate that out here. And we get the pressure of oxygen, 4.59 atmospheres.